Yeah, hello everyone. So I think this time's class we are uh, holding it online because of the Diwali celebrations, and I think some of the students are not here. So I'll uh, be posting the videos online and for a couple of classes. Yeah, so let's get started. I think we stopped in the middle of timestamp based concurrency control, and I'll revisit this part from beginning. Right, that is from where we stopped. Right? And so just give me 1 minute and let me try to adjust my screen and yeah. Okay. Uh, okay. So what is this timestamp based protocol? So timestamp based protocol says that whenever a transaction comes, we'll allocate it a new timestamp, right? And this timestamp is based on a first come first serve basis, right? For example, let's say that there are a bunch of transactions that come in, and we allocate them these timestamps that the first guy gets a timestamp of 1, the second guy who comes gets a timestamp of 2, and so forth. So it is unique. Every timestamp gets a unique number, right? And the other thing that's interesting about this protocol is that uh, if a transaction aborts at any point, it'll restart at a later point, but it'll get so think of this like a queue, right? So people are standing in a queue to get into a bus, and somehow one person gets kicked off the queue, right? For whatever reason. Then that person goes to the back of the queue, and that person gets a new times, right? So a new order in the queue. And that's what this timestamp based protocol has. That's something unique about this timestamp based protocol. That if some person gets aborted, some transaction gets aborted for whatever reason, it restarts with a new timestamp. Okay, and whenever a timestamp, whenever a transaction completes, right? Let's say you find an order in which transactions are completing. That is, they did not get aborted, but they're committed, right? That is the order of serialization. Okay, that's the serial order, which is conflict equivalent to the actual order, right? So that's the order that we need, that we are looking for, and we'll also look at something that's unique about these things. That's unique about this specific protocol that we have not seen so far. We'll look at all that. Okay, so let's look at a high level overview of this protocol, and then I'll reason why this in fact serial, right? Why this protocol actually works. So for this protocol to work, with every data item, right? With every data item, there are two things that are maintained. One is the write timestamp and one is a read timestamp. Okay, one is a write timestamp and one is a read timestamp. And these transactions, when they're trying to read or write, one of the things they check is that is there a conflict, right? Is there a conflict? And previously, when we are doing lock-based protocol, for example, conflicts were checked based on is some other transaction holding on to a lock, right? So that was the core idea behind uh, should I allocate the lock or not, and based on that, does this instruction continue or will it have to wait on some other transaction, right? Which is holding on to some certain locks. Here it's different. Here there are two things. There's a write timestamp and read timestamp, like I was mentioning before, and there's no waiting here at all. If there is a conflict, then we'll abort and we'll restart. Okay, that's the idea. So let's define what is a conflict here. Okay, and let me take this up with an example. Okay, let me take this up with a simple example, or maybe even intuitively, let's look at a couple of transactions. Okay, let's say that there is a transaction TI here. Okay, and let's say that there is one more transaction TJ here, and there's a data item X. Okay, and what we mentioned before is that if a transaction completes and executes successfully, right? Let's say TI executed successfully, followed by TJ, right? That is TI successfully completed and committed, and TJ committed as well. Then what we're claiming is that it doesn't matter when TJ committed. Maybe TJ committed earlier than TI, right? We are nevertheless claiming that serialization order is TI followed by TJ, because TI came into the queue before TJ, right? So So in this case, let's say I'll make it clear, I is less than j, because I is less than j, I is older, right? Ti is older, right? And Tj in some sense is a newer, right? Now, because of this property that if both of these are successfully committed, then we're claiming that in our serial order, Ti is going to happen before Tj, right? Because of that, what property do we need to maintain in terms of this graph? We can only have an edge, right? We can only have an edge of this sort, right? We can only have an edge of this sort, an edge of edge that is from a transaction Ti to Tj such that I is less than j. We can only have edges of this sort. If at all there is an edge of this sort where Tj is trying to I mean, is in some sense it's in conflict with Ti, right? That is, it is trying to read or it's trying to write something that Ti, for example, has read, right? For example, or wants to read rather, sorry, wants to read. That is, Tj has a write of x, and followed by this is here, followed by this Ti asks for a read of x, right? In this case, there is a dependence on Tj, right? The Tj has to happen before Ti, and such a thing should not happen, ideally, right? This thing should not be allowed in our timestamp based protocol. And if this thing is happening, then what we will do is that we will abort Ti. We'll say that Ti is trying to read something from the future, right? So we say this is timestamp because each of these i's and j's that we're speaking here are all in some sense indicative of the time in some sense, right? So this uh, Tj came from the future and Ti has read something, is trying to read something from the future, which should not be allowed because it's going to break one of the properties, because of which we'll abort Ti at this. We'll abort this. Okay. So in some sense, whatever we will be discussing, we'll be discussing with respect to this. We'll be respecting this, with respect to this. And I want to also emphasize again back to our table, right? What are the this is the conflict table. Two transactions conflict on. I want to re-emphasize this. I think this was discussed a couple of times already. If there is transaction Ti and Tj, they do not conflict. No conflict here. When both of them are reading the same data item, there is no conflict. But if there is read and write, yes, there is a conflict. Right? If there is read and write, yes, there is a conflict. And definitely, of course, write and write also have. Right? So this is something that we should be careful about. Right? And this table is something that we'll again be utilizing here in order to understand this. Right? So now we have this read and write timestamps, and somehow we want to reflect what is happening in this table through this read and write timestamps, right? So let's take a careful look at what can be done here. Okay. So let's start with some data item x, and let's say it has a read timestamp, and sorry. Let's say this is the data item x, and I have a read timestamp, and I have a write timestamp. Okay. And let's say that at some point of time, there are some reads and writes that have happened. Whenever a read successfully completes, then we update this read timestamp to whatever is newer, right? For example, let's say that I is the latest transaction, Ti is the latest transaction that has read this data. Then we will update this as I. If Tj is the latest transaction that has written to X, has written this data item X, then we'll update this as J. And at a later point of time is Tk, which is newer than Ti and Tj, right? If this guy comes and this guy is trying to read this data, right? So it's fine because so far there's no conflict. Ti has read data, Tj has written data, right? Tk is reading from Tj, right? So in some sense that's the dependence that is there, but this dependence is in some sense valid. Like it's a black dependence. It's not this red in color. That is, we are not going back in time, right? Because of which it should be allowed. And Tk is, as I was mentioning, is trying to read. So it's fine. So we'll update this read timestamp instead of I, it is now 4. Okay. That's all we'll be codifying. But what would not be allowed is that, let's say that there is th, which is before I, j, okay? And if this guy now comes and this guy is trying to read or write, then there is a conflict, right? If for example, at this point, if this guy is trying to read of X, then what will happen? What will happen is that currently K has already read. So now there is an edge, right? This is a red colored edge from K to H, right? And this is not allowed. And this is what we'll be checking. And the check is very simple. If you look at it, if this timestamp here, if this is older than whatever has been read or written, okay, whatever has been read or written, that's all we need to check. Sorry, reads don't have conflict. Sorry. So I did write something wrong here. Just give me 1 minute. Let me update this. In fact, so actually the conflict is not with the read. So even if a transaction has read something, there's no conflict there. The conflict will actually be with very specifically with respect to, in fact, let's try this, right? Let's try this. So, in fact, the conflict is in fact with respect to something else. It is with respect to a different transaction, and let's write it carefully. So if you look at it, read and read don't conflict. So the red arrow is not from this. Instead, the red arrow is from the right guy, which is also, you know, if you see J is also ahead in time. So actually, the conflict is from J. So this is the fact, and this is where the conflict lies. Okay, because of which TH nevertheless has to be aborted. Okay, so the next step here is aborted because TH is now out of order. Okay, so let's now try to codify this a little further using algorithm or a pseudocode per se. We'll just write it. So when does a read when is a read successful? When can I update my data structures, and when should I abort? Right. So that's the question that I'm asking. Like we were seeing before, if it's an older transaction, okay. So what's the property about an older transaction? If I have Ti and Tj, how do I identify which is older? So if Ti came before, and let's say that Ti came first in the row and Tj came second, right? So I will be 1. J will be 2, right? So J will be, if J is greater than 1, it is older, right? So the way to identify if I is less than J, then I is older than J, right? I is older than J. So now what we have to, what is the check that we need to do? So the check is simple, right? So because read and write conflict, read and read don't conflict, we should only be checking with respect to the right timestamp. Okay? So what we are saying is that the this TS is basically this function stands for the timestamp. The timestamp of Ti, is it less than or equal to the right timestamp of Q? Okay. So that's the question that we are asking. Because in this case, if TS is it's a really old transaction compared to when the write has happened. In that case, this is like a read from the past, right? So a write that has already happened in the future. Some transactions trying to read. It's like a red edge that we're introducing. It should not be allowed, because of which TI will definitely have to be aborted and rolled back, and we will restart this transaction with a new timestamp. And this new timestamp is again think of the queue wherever it has stopped right now. After, let's say, Ti, Tj, Tk, Tl, and finally after Tl, now a new this Ti, because it got aborted, Ti will become Tm. Okay, the instructions within Ti will be the same. Whatever it wants to do will be the same, but now it's Tm. Okay, and we'll again try to execute. We'll again try to. So that's what this what do you say? This check basically ensures. And if this check succeeds, that is, it's a newer transaction which is trying to read something that was written by an older transaction, right? So that is, this Ti is newer compared to whatever wrote this data item Q. Then we should be able to, we should definitely be updating it. But the only thing that we should ensure is that the read timestamp is correspondingly updated, right? So this is what we will now be doing. Okay, so we will look at this update as the read timestamp of Q and this new transaction Ti, right? Whichever is newer, and the newer, like we are mentioning here, is the max, right? Max is newer because older is lesser, and I mean a lesser value indicates an older value, right? So we'll just be doing a match operation. Okay, now let's look at a similar thing for write. Again, write is very similar to read, except that write, if you look at this table here, right? When we look at this table here, a write conflicts with what? A write conflicts with read, a write conflicts with write as well. Yeah, right. I mean, you can look at either of these. Write conflicts with write as well as write conflicts with read. So write conflicts with everything, right? So our check here, because this read was conflicting only with write, or check was only with the write. But now, because this write conflicts with both, right? We should be checking both the things, right? So that's what we'll be doing. Okay. So our check is simple. Okay. So this is the first check, which is same as the read, right? Which is the read-write conflict. And if that happens, we'll again be aborting and coding. And the same thing is again here. Okay. So this thing just says if my read, if my write that's happening should have actually happened in the past, right? That there is a newer write that has already happened, and I'm going to overwrite the value, which is not allowed. In that case as well, I will be rolling it back. I'll be rolling it. Now, if these two conditions have not happened, then all we need to do is we need to again update the write timestamp with that of the new one, right? With that of the new one. But this time we do not need to check the max operation, right? We do not need to check the max operation because this, this thing already ensured that the timestamp that is writing is already a newer one, right? So it's already the max is the TS I guy. So we'll update this write timestamp to TS, right? So this is in some sense simple, but I want to actually argue further that there won't be these red lines, right? And for that, let me actually skip a little, and I'll get back to that. Okay, I'll get back to the previous two steps, and first I'll just argue about the theory, right? I'll just try to put forth what's the argument there. Okay, so the two checks that we did, right? Two checks that we did are ensuring that if there was a transaction of this sort, right? If there is a red edge, then my claim is that all those red edges will be aborted. Yeah, will be aborted. And how do I ensure that? I currently am only considering read and writes. I'm not considering a more updated data structure or more inserts, updates, and so forth, more operations rather. And because only I have these two operations that I'm allowing, right? Because of that, now if there is a transaction which has this red edge, right, it can only be introduced through either reads or writes. And like I was arguing before, if the moment we find this red edge, right, we discard this transaction, right? We discard the newer transaction that is there. That is in this case, the larger transaction guy is essentially the newer guy, right? And this is the older guy, right? Older guy. And the moment this happens, this red edge gets introduced, this newer guys, we decide to abort. We decide to abort. So we are in some sense good just by the simple protocol, right? We are ensuring that there exists a serial schedule that's equivalent to whatever we are doing just by doing this, right? Okay. So now let me get back with a concrete example, right? Let me get back with a concrete example and update things, right? As we are doing things, let's update it. Okay. Now initially I'll just update this whatever is here, right? Whatever is here, I'll just update. The read timestamp of A is 0. The read timestamp of B is 0. Write timestamp is 0. Write timestamp A is 0. So what I will do, I'm going to cut these two things here, right? Let's use these two lines, or maybe not, right? Maybe I won't use this. I'll use something else here, right? I'll use read write right. I'll use read write, and this is for A, right? This is for A, and the right side is for B, right? So there is some space here. Again, I use read, I use write. Yeah. Initially, what are they set to? They're all set to zeros. Okay? They're all set to zeros because whatever happened in between 0 all the way to 25 has returned data items or read data items other than A and B. Okay, let's assume that. And A and B are now being read between transaction T25, T26. There is some read write operation. Right? Now let's start with this first step, which is read of B. When read of B happens, what is the first step we need to do? We need to check if there is a conflict with respect to any transaction that has returned. Okay, so write of B is from 0, which is a transaction way in the past. So we are not in conflict, but we have to update the read of B. We'll make it 25. Okay, so we're fine. So we'll make it 25. There's no conflict. So nothing is fine. Next, what did we do? We read B. Okay, we read B again. This time it's 26. Again, there is no write. There is no problem. We'll update this. There's no conflict. Okay, no conflict. We are at 26. We'll do some internal operations which you don't care about. That's fine. It's doing something and we are oblivious to it. It doesn't matter what it does. And it will write back. And now we again need to check. And in this write, we will check both the read timestamp and the write. We are trying to write 26 to the right value. So we have to check if 26 is greater than 0, greater than equal to 0, and 26 greater than equal to 26. Turns out that it is true. So there is no issue here. So we'll write 26. Okay. So far good, right? So far we are good. Now we'll come to the read. Now when we come to the read, what happens? The T25's read is here. So the read, I'll try to look at this. Is 25 greater than 0? Yes. Sorry, we don't check the read timestamp. Sorry, we check this write timestamp. Is 25 greater than 0? Is yes, that is true. Only read and write can conflict. So we'll update the read with. So we are fine so far. And finally, there is another read here. And again, this is read from 26. 26 now tries to read the data here, and we'll again check the write timestamp, right? And we are fine here again. Okay, we are fine. So we can update it to 26. Finally, there's A is A plus 50, some internal operation. Finally, a write. Right, and when the write comes, I have to check both the read timestamp and the write timestamp. Is 26 greater than equal to 26, which is the read timestamp? Yes. Is 26 greater than equal to 0, which is the write timestamp? Yes. So we are fine. We can write. Okay. We can write. We are fine. In the meanwhile, there has been a display, which I think it has happened, which doesn't update this database state right now. Finally, there are these two displays, right? There's display, and I mean, both the commits have happened. And both the commits have happened. So right now there is no issue here. Yeah, this transaction is fine. This schedule is fine, and this schedule is valid under timestamp based protocol, right? This is. How about this schedule? Let's try to look at this queue again. There's just one element here, which is queue that is needed. So this time I'll only have one table here, and this stands for the two data element. First, initially, it's like it mentioned, I'm storing zeros in here, right? Like this mentioned here. Now T27 is trying to write. So what is the check we will do? Because it's a read, we'll only check the write timestamp. Is 27 greater than equal to 0? Yes. 27 is greater than equal to 0, we are fine. Right? Okay. So what will we do? We will take this. We'll update this as 27. Now again, 28 comes in. 28 is again trying to do the same, right? 28 is again trying to do some operation on Q, but this time it's a write. So when it's a write, I have to check both the read timestamp and the write timestamp, and what is being written? 28 is being written. Is 28 greater than 27? Yes, true. 28 greater than equal to 0? True. So I can write. Okay, so far there's no issues. So fine. Now again, a write comes, and this write is something that is interesting, right? This write is interesting because when this write comes in, this is now 27. Okay, this write again can conflict with the read or write. Is 27 greater than equal to 27? Yes, we are fine with respect to read. Now let's check, is 27 greater than equal to 28? No, it is not. Right? And why is that? Because this read and this read conflicts, and this is indicated by this conflict, right? It's indicated by this, this inequality that 28 is greater than 27, right? So this was not, in fact, less, like 27 was not greater than or equal to 28, because of which what we'll do, we'll have to abort at this. Okay, this is aborting here. This is aborting here, and T28 in fact can successfully write whatever value it wanted to write, and it's fine, and it's okay, right? And in fact, this is a very weird scenario that this is a blind write, right? This, in fact, if you, I mean, like we were defining before, this is a blind write. Okay, so I hope that it is clear so far. Well, I forgot to mention early on in this slide that, or before I started this lecture, that whatever questions you have, you can either drop me an email, or we'll discuss this on the next Wednesday in the next Wednesday's class, or you can also come by to the office hours, whichever is convenient, whichever is convenient. And if you want to meet me in person, other than the office hours for this week, especially for this week, because we are off schedule in terms of how this video lecture is being recorded, you can also drop an email, and that is fine. Okay, so I hope that it's clear so far. We'll take another example to make it very clear. So this time, how many elements are there? There is W, X, Y, Z. Okay, there is W, X, Y, and Z. The first line of this transaction here. So the first line of W will be a read. The second line will be a write. Okay? So I'll write this in 2 lines, and I'll keep writing this. Okay. So let's start with this first line. The read of X. Initially, everything is set to zeros, right? Like we were mentioning before, everything is set to zeros. And T5 is trying to read X. Is X is 5 greater than or equal to 0? It turns out that it's true for everything, but this time it's just a read, and read write do not conflict. So this is the check we'll be doing. So we'll update this 0 to 5. So far, there's no conflict, no issues. T2 is now trying to read Y. Again, there is no issues here, so we'll just update the read. Again, T1 is trying to read Y, right? So this time again, there is no conflict because this 1 is greater than 0. Okay, this is the check that we'll be doing. Is 1 greater than or equal to 0? Yes, it is greater than or equal to 0, so we don't need to check. Okay, but the interesting thing here is that among 1 and 2, right? 2 is newer already. 2 is newer, so we will not be cutting this and writing 1 here. So we'll not be updating it as 2. It has 1 because 2 is already read. Okay, so far good. Let's go to this T3 now. T3 is now trying to write Y. Okay, so now we have to check both the read and write timestamps. So if you look at the write timestamp here, the write timestamp is 0, read timestamp is 2, and 3 is greater than both of these, because of which I can happily write this. So this write does not conflict with anything. Let's now look at this write of Z. Well, both are zeros here. Both these are zeros. So I'll update the write timestamp to 3. And there's no conflict so far. 3 is greater than both the zeros. Now there is a read of Z. Okay, there's a read of Z. So in fact, this read only needs to check the write timestamp. Is 5 greater than or equal to 3? That is this read T5? Is it later than the read T3? Because 5 is greater than 3? Yes, it is. It's a newer transaction. So we'll update this to 5. So far, we are good, right? So far, we are good. There's no issue. Now there's a new read that has come in. Okay. Now this read has come in, and this is from transaction T2. Okay. Now let's take a careful look at this, because this read can only conflict with write. Okay. And this is the right value, right? Who has written? 3 has written to Z. That is the latest transaction that has written into Z. And T2 is the older transaction compared to T3, right? Because T2 is the older transaction compared to T3, there is a conflict. And if there is a conflict, under this model, we will abort, right? So our next step is that we will be aborting. So this T2, basically whatever we did here needs to be rolled back. Okay? We need to undo everything. So this was where it aborted. We'll undo everything that it did. Okay, so T2 is aborted. We'll now continue transaction. We'll now continue this schedule. We'll now continue the schedule and see what happens. There is another read here, and this time the read is on X, and T1 is trying to read. Let's go to X, right? And when we see X, no one has written. No transaction has written into. In fact, I shouldn't be saying no transaction. T0 has written into X, right? T0 has written into X, and now T1 is trying to read X, and there's no conflict because T0 is older in nature. But note that we will not be updating this 5 here, because 5 is newer than 1. Okay, there's no update. Similarly, we'll continue ahead. This is a write of W. So this time I'll be a little. I'll try to be a little. Sorry, there's a read of W, and this time I'll be a little faster. Let's look at W. W is here. There's no conflict. This will become 4. This time there's a write, and the write is from. Okay, when there's a write, we have to check both the read and write timestamps, and there's no conflict with respect to write. Note that 3 is newer compared to 0, but there's a transaction from the future. There's a T4 that has read something that T3 is trying to write into now, right? So in some sense, if you were to use the terminology that people use in this timestamp based protocol, this write was needed in the past. And this write was needed in the past, and so it cannot happen. So there is a red edge that's being introduced from T4 to T3, and so T3 has to be aborted, right? So we'll be aborting this guy. This abort basically also means the same thing. Whatever transaction was done, whatever this transaction has written to, whatever it has done, it needs to be undone, right? And this is the abort, right? It has to undo everything. Okay, so this is so far well and good. Now we'll continue ahead, right? Let me scroll down a little. Let's continue ahead with T5. T5 writes further, right? T5 is writing into y, and let's look at this. There's no conflict because phi is greater than both 2 and 3. So we'll just update y's timestamp. Finally, there's a write of z. Write of z again, phi is greater than or equal to both of these. Phi is greater than or equal to phi. Remember the equal to, right? So it's true, it's true. So this is fine so far, and we have aborted 2 transactions, 3 of them successfully executed. Okay. Now, I'm hoping that this part is clear so far. Okay. Please do rewatch in case something is not clear, and still if you don't follow, please do come. So based on this example and also this explanation so far, let's argue something, right? That first of all, there is no deadlock, right? So why is there no deadlock? There's no deadlock because there is no locks. Okay, deadlock only happens if a transaction holds on to it, holds on to some resources, right? In this case, we're not holding on to any resources. In fact, there's no locking it. So definitely there is no deadlocks. Okay, so hence no transaction waits, in fact, right? So there is no stagnation, anything of the sort. In the traditional sense, that there is a transaction that's waiting for anything. There's no that's not a problem, right? Now let's now argue about this. Is this schedule cascadeless, right? Are there cascading rollbacks, or even for that matter, because cascading rollbacks, basically this whole notion that you have to abort one guy, you will have to abort some other guys, right? Some other transactions that are dependent on these transactions, right? This whole notion is linked to recoverability. So let's argue about both these things, right? First of all, let's argue about this transaction that we just saw. Okay, what are the things that we are in fact, undoing here? We are in fact undoing both T2 and T3, right? We are undoing T2 and T3 here, right? And let's look at what all these guys have done, right? What all these guys have done when they got aborted. Okay, this guy just did reads, so we are fine. But now this, what has T3 done? T3 has done a write of Y, T3 has done a write of Z, and T3 has done a write of W. Okay, so let's look at, has any other transaction read from T? Okay, let's carefully look at this read C. I want you guys to take a careful look at read C, because what you will realize is that whatever T3 wrote, right, T5 has read from that. T5 has read from that, and it has done something else with it. I don't know what it has done. It might have done some internal operations like z equal to z plus 20, z equal to z plus 30, whatever. Or maybe it did x plus z and wrote it into y. I don't know what it did. It did something with it. But that's the problem, right? Because it did read the value after T3, and T3 got aborted. But T5 continued and it even committed here. Maybe I'm going to assume that there is a commit here. And when it committed, it has read something that is transient in nature, right? It has read something it should not have. And that is a problem, right? And that is a problem. And this problem that we have seen is an example of a schedule that is not recoverable, right? This is not recoverable. And the way to handle this is, if T3 aborted, we should be aborting T5, right? And that is something that we'll be looking at in some of the later slides. That we'll be looking at slides. So this is, so to summarize this, to summarize the point I was making, this timestamp based protocols, they do not take care by default, they do not have this notion of cascading rollbacks, right? They do not have this notion of cascading rollbacks, so they are free of cascading rollbacks. But because they are free of cascading rollbacks, they in fact do something worse. They in fact are not recoverable at all, right? They're not recoverable. the ideal thing, if this was were to happen, is that we should have actually aborted T5. We should have aborted T5 and made sure that we do allow a cascading rollback, thus ensuring recoverability. Thus, we ensure that that schedule is recoverable, right? But we have not made sure of that. So our idea now is to somehow incorporate this notion of cascading rollback and somehow make sure that you know either we make sure that this schedule is cascade free, it's free from cascading rollbacks, or if cascading rollbacks need to happen, we somehow take care of that, right? Now let's start with the solution 3. Yeah, let's start with the solution 3 because this is something that I think for the people who are in the class, right? I think some of you were in the class and we did discuss this point briefly when we were speaking about this, timestamp-based protocols. One simple idea is that you note down that what all transactions has T5 read from. For example, each transaction has read from. T5 did read from T3. So you update T3 as a dependence for T5. Only if T3 successfully completes its execution will I commit T5. Okay. So if, for example, T3 has not committed yet, right? For example, let's say that there was no abort here and it was still executing at this point. While this has completed its execution, we will wait till T3 commits. Once T3 commits, and we'll remove T3 from the commit dependency from T5. And if T5's commit dependencies are empty, that is, all the transactions that it depended on have completed execution, we will commit. Okay, we'll commit. Now, this is the most simple one in terms of if you were to think of it. Okay, if you were to think of the solutions, this is the most simple one, but it's a little complicated to execute, and it also has cascading rollbacks, right? You also have to do, if something aborts, then what all read from the writes of this transaction all need to be aborted. So this has cascading rollbacks, but at the same time, advantage is that it is recoverable. Okay, now let's look at some of these other solutions that are being. Okay? So the other solutions are simple. Okay, these are very specific in some sense as well. So if, for example, I read later dependent upon the previous write, then these solutions may not work as well. But the idea is simple. Okay, if there are writes, you push the writes all the way to the commit. Okay, you push these writes to the place where there is a commit, and at that point you can either do locking, okay, limited form of locking. That is one idea, that whenever you're writing something, okay, you create this small lock. Okay. The other idea is that if you're trying to write something, okay, you make sure that it is atomic, right? You write the whole thing. No other transaction is trying to read at that point in the middle and so forth. Right? It is just trying to write in the middle and so forth. Okay. So this is again very similar to this solution 2 and solution 1 are very similar in nature. One of them is using locks to implement what one is is actually recommending and so forth. Right? Okay. So probably this is the first part that I wanted to cover in this thing in this section. In fact, I can in fact go a little ahead in this. Probably it will be in some sense interesting as well, but because of lack of time, I unfortunately think that maybe you should stop at this point, right? At this at this part of this chapter, and leave the rest for you guys to read. It won't be, any question post this point will not be asked in your exams, but only till this part, right? This timestamp based protocols, right? Only till that part will be asked, right? Okay. So I think I'll stop this. I'll upload this video and then let's continue with the next one later, right? Yeah. Yeah. Thank you.